positive number. Okay. So we have to do here we take this terms, then this convert here and it converts this to 1. That is limit reference a to the power 1 by n goes to 1 for positive a. So case 1, the trivial case if you take a equal to 1, then what you will get? If you are taking a equal to 1, ready 1 by n, you are only getting 1 as a number, so the sequence is a constant sequence 1 1 1. So obviously that will converge to 1, nothing to do. So this is the trivial one. Trivial case. Now the case 2 where I take a greater than 1. Why I am taking these two separate cases? Because it is simply a greater than 0. Okay. So this can be, the number can be either greater than 1, equal to 1, okay, or less than 1. So three cases we have to consider. The first one is equal to 1, that is done. Then a greater than 1, case 3 I will take this one, that is a greater than 0 as is given, but it is less than 1. Now just see first the case 2. So if I take like this, then a to the power 1 by n is also greater than 1. Obviously. Now if it is 1 greater than 1, then so specifically a to the power 1 by n I take a 1 plus xn. That means if you vary this n in the natural number set as we do this sequence, then you are going to get obviously all greater than 1 numbers. So I now just write it as 1 plus some positive number xn. Okay, so where xn is greater than 0. That means xn here is now giving you the recurrent form. If you vary n, this xn will vary. That means with 1 you are adding some positive quantity, okay, which is varying with the variation of the natural number you are taking. So a is this thing, a to the power 1 by n equals to this one if I claim, then a is nothing but the whole to the power of n. Okay, now if you expand it binomially, then you can get this expression as is shown in the box. Okay, so 1 plus nx plus some positive numbers plus some other numbers, it will go on and it will contain n plus 1 terms. So obviously x is positive. Here I have written x, that means here I am trying to denote it as xn. So as xn is positive, so obviously this all terms you are getting as positive. So if I now consider only the first two terms, 1 and nx, that is 1 plus nx. So definitely that is 1 plus nx is lesser than this whole expansion. That means this whole expansion means this left hand side, that is 1 plus x to the power of n. That means if I write 1 plus nx on one side and 1 plus x to the power of n on the other side, then definitely this greater than symbol or greater than sign will hold. That is 1 plus x to the power n will be greater than 1 plus nx, as x is greater than 0. Here you just read x as xn as is written here. So this is what they have claimed here. This one is greater than 1 plus n into xn for n greater than 1. Okay. So now you choose epsilon greater than 0. So what was our aim? Why? What we are trying to prove? We are trying to prove this limit is equal to 1. That means, as we have done before also, we will try to find out at least one natural number, such that once we exceed that natural number, no matter what element or what sequential element you take, it should lie within a small neighborhood of the limit point. Here limit point is 1. Okay, so that's what we are trying to do here. Okay, and for that, what is the fundamental starting point? We have to choose any positive epsilon greater than 0. So we are starting with that. So let epsilon greater than 0. Then as we do in the definition, we take the difference between the limit point and any sequential element. That means here a to the power 1 by n. So this thing. Then we forcibly put lesser than epsilon. Okay. Now we see when this will hold. That means when it will hold, if we just break it, we will get if a minus 1 by a minus 1 by n less than epsilon. Okay. If this is true, if n greater than a minus 1 by epsilon, that's, we are just simplifying it. Nothing specific about it to mention. We are just simplifying this thing as far as to find out the n for which we will be working. Okay. So in case we do that thing, here what I am getting, see here, a has been expressed as a greater than 1 plus n xn. So a minus 1 by n is greater than xn. Okay. So this xn here we are using from here. What is xn? Xn is a to the power 1 by n minus 1. So here actually we are getting a to the power 1 by n minus 1 as xn. If you use it here, we are all total getting this relation which is claimed here. Okay. So k, if you take the natural number as the box function a minus 1 by epsilon plus 1, and obviously once we take any natural number which is greater than k, obviously this expression forget about this expression. First, let us take this expression. This expression will be less than epsilon. That means in turn, this expression will be less than epsilon. That means in turn, this one is turning out to be the limit point of a to the power 1 by n. Okay. So this is then proved key for a greater than 1, the limit of the sequence is 1. That means the sequence is convergent and converges to 1. Now, let us take the case 3. So a is now lying between 0 and 1. So we take b as 1 by a. So if a is less than 1, then you take the inverse, that means the reciprocal of it. Definitely then that reciprocal number is greater than 1, that means b is greater than 1. Now once b is greater than 1, then it falls in case 2 only. Because here a was nothing specific was mentioned about it. Only a was greater than 0 and in case 2, a greater than 1. Okay. So we have now got obtained b just as we have constructed our b. B is matching the property of case 2. So whatever we said for case 2 is now applicable for b. Okay. So via using case 2 we can claim limit n tends to infinity a to the power 1 by n. This is again by the algebra of limits. This is equals to the limit of 1 by b to the power 1 by n. But what is the limit of this denominator? It is 1 by case 2. So 1 by 1 is 1. Okay. So limit n tends to infinity a to the power 1 by n is 1. So combining all the three cases, we are saying we are in each and every case we are getting 1. So here the limit point is 1 only. So it is true. Now another one, suppose xn itself is a sequence which is converging to 0. That means it is a null sequence. And now we are provided with a positive number, a greater than 0. Then what we have to prove is the sequence which is generated by taking a to the power xn. That means xn sequence is already given, a specific, any positive number is given. Now you are generating a sequence a to the power of x. That is the exponential sequence we are generating. Okay. So here what the new sequence is generated, we have to prove it is convergent, and here also it converges to 1. Okay. Then what happens? This we will see in the shortened corollary. A to the power xn if we take, and if suppose xn is converging towards L, then limit of a to the power xn is equal to a to the power L actually. Whatever is the limit coming here will be just transferred to the limit here. Okay. So here L being 0, a to the power 0 is 1, so we will be getting 1. Now let us see how we proceed with this proof. It is already given the limit a to the power 1 by n equal to 1 from what you have proved in the first problem. Okay. And also limit a to the power, if limit a to the power 1 by n equal to 1, then if you just take the reciprocal of it by algebra of limits, again limit a to the power 1 minus 1 by n will be 1. Okay. So now let us choose epsilon greater than 0 and let us use the definition of limits for both of them. That means what? For this one we will find for natural number such that this relation holds. A to the power 1 by n is lying between 1 minus epsilon to 1 plus epsilon for all n greater than equal to k1. And again for this sequence, again we will get some other natural number k2 such that again the definition holds. That means a to the power minus 1 by n now lie between 1 minus epsilon to 1 plus epsilon. Okay. Now this is holding for all n greater than equal to k1 and this is holding for all n greater than equal to k2. Okay. And in general k1 is not equal to k2. So if you want if this relation and this relation will hold simultaneously, then we have to take k as a maximum of k1 k2. So suppose it is holding for k1 is 5 and k2 is 7. So this relation is true whenever n is greater than equal to 5. This relation is true whenever n is greater than equal to 7. So if I now want both of them to be true, then you just take n greater than equal to 7, then this is true, and as n greater than equal to 7 means n greater than equal to 5 obviously, so this is also true. So that's why we take the maximum of k1 k2. Okay. So as soon as I take maximum of k1 k2 for every n greater than equal to k, this relation and this relation holds together. That's what they are written here. Okay. So if you take k also particularly, then this is also true because we are saying for every n greater than equal to k, this is true. So for n equal to k particularly, this is also true. So I have written this. Now it is given the limit n tends to infinity xn equal to 0. That is whatever the definition is already provided there in the problem. Okay. So So again, let us apply the definition. So we will find the natural number p such that for any epsilon, so whatever epsilon we are working with, we will use this here also, or I can use some other epsilon also. What they are using here, they are taking 1 by k as a epsilon here. Okay. What is k? K is a natural number. So 1 by k is obviously something lying between 0 and 1. Okay. So for that, epsilon equal to 1 by k, since limit n tends to infinity, xn equal to 0, definitely we should find some natural number p such that once n is greater than equal to p, all the sequence elements xn should lie between minus k to 1, minus 1 by k to plus 1 by k. So that is holding good here because 0 is the limit. Okay. Now let a greater than 1. Now if a is greater than 1, then obviously this is true if this relation holds true. Why? Let me just write it separately. So suppose you are taking two numbers x greater than y, and you are taking any greater than one number, say t, then obviously t to the power x is greater than t to the power y if it is given x greater than y. If you just take a numerical example, so t equal to 2 you are taking, x equal to 4 taking, and y equal to 1 I am taking. Okay. Then what is t to the power x? It is 16. What is t to the power y? It is 2. So you can just simply check if t to the power x is greater than t to the power y. And here x is greater than y. That means whatever relation they are maintaining, if your number given is greater than 1 here, then obviously when you apply this number as an exponent of the given number t, then the same relation will be maintained. That means same ordering will be maintained. X greater than y, then t to the power x greater than t to the power y. If your t is given to be greater than 1. And just the opposite holds if t is given to be less than 1. That means whatever relation, if I take t less than 1, any number is provided to me, then the opposite happens. That means, but why opposite I am saying? X greater than y is given. This is the ordering between x and y. But now if I apply them as exponents over t, that is t to the power x, t to the power y, then the relation, that is the ordering relation, just get reversed or converts you are getting. That is opposite you are getting. That is, if t less than 1, then definitely t to the power x is less than t to the power y, whenever x is greater than 1. So just these two things they are applied here, they are applying here. Okay, let us see. So a greater than 1 if I take. So as I discussed, this should come. Why this should come? Because of this relation. A is fixed. Then you are taking this as the exponents of a. You are taking a to the power minus 1 by k. You are taking a to the power x. Then you are taking a to the power 1 by k. As your a is greater than 1, so this relation will be maintained for the exponents also. Okay, that means a to the power minus 1 by k should be less than a to the power x, should be less than a to the power 1 by k. Okay, and when this is true, this is true whenever this is true. That means this relation is true as long as this relation is true. But this relation is true not for all n, but for n greater than equal to p. So obviously by chain rule, this relation is true for all n greater than equal to p. Now it is given this relation in turn is true whenever I am taking this relation to be true, but this relation in turn a to the power 1 by k is lying between 1 minus epsilon to 1 plus epsilon. Similar is the case for a to the power minus 1 by k. Okay, so once I am getting these two things, a to the power minus 1 by k is greater than 1 minus epsilon, so I will use it here. And again, a to the power 1 by k is less than 1 plus epsilon, so I will use it here. Okay, so this one part of this relation and another part of this relation is used here. So as a result, you are all getting this thing, and this is holding true again for all n greater than equal to because of this one. Okay. Now let us take the reverse one. Reverse means now I am taking a is less than 1. Again, as I explained, if a is less than 1, whatever relation you are getting here, whenever I will use them as an exponents of a, this relation will just get reversed. That means this less than will become greater than, and this less than will be becoming greater than. Okay, that means what will happen now? A to the power 1 by k, let me just see here, a to the power 1 by k will be less than a to the power xn, okay, will be less than a to the power minus 1 by k. And again, it will hold true as long this is true. That means it will hold true for all n greater than equal to p. Okay. Again, using this part, a to the power minus 1 by k is greater than 1 minus epsilon. So here it is coming, sorry, not this part, but this part, 1 minus epsilon here. a to the power 1 by k is greater than this thing, so I put it here, and a to the power minus 1 by k is less than 1 plus epsilon, so I put it here. So as altogether I get this relation. So you see, no matter whether a is greater than 1 or a is less than 1, you are always getting this relation. A to the power xn is lying between 1 minus epsilon to 1 plus epsilon. That means you just take now this 1 minus epsilon less than a to the power xn less than 1 plus epsilon. If you see, if this is actually giving you the definition of the limit of a to the power xn as 0, because just simply they have sorted it, these three things out: 1 minus epsilon less than a to the power xn less than 1 plus epsilon. That means this gives you mod of a to the power xn minus 1 less than epsilon whenever n is greater than equal to 3. But this claims ki a to the power xn sequence is having the limit point 1. So this proof is done. So as I said now, the corollary follows obviously. If I now take, instead of the null sequence, there I have taken null sequence in this problem. Limit x tends to infinity, xn was 0. But now if I take L, any L can be 0, L cannot be 0, okay, for anything. And A is a positive integer, a positive number, don't need to be an integer. So a positive number you are taking. Then the new sequence which is created via this sequence, okay, a to the power xn will also be convergent and will be convergent to a to the power n. Simply you just see this limit is carried forward to the exponent of it. Just like that it is happening. And how is it happening? We have just explained it. Okay. Similarly, here this also follows. If you now take, instead of a you take e. Okay. So e is also positive number. So again the same thing follows. So limit n tends to infinity e to the power xn is nothing but e to the power l, where limit n tends to infinity xn equal to. So actually these are some of the very important limits which can be used in some problems. Okay. Now let us do another result. Why this result is important? So suppose a positive sequence of numbers is given. Another thing let me mention here, they are mentioning the positive real numbers. This is an extra information there, because obviously if you are saying positive, definitely it has to be real number. Complex number cannot be ordered, cannot be said to be positive or negative. So it is meaningless to say real number again. Okay. So let even be a sequence of positive numbers such that, this is important, the ratio of two consecutive terms in the sequence you are taking, un plus 1 by un. That means suppose you take n1, n equal to 1, that means u2 by u1, then u3 by u2, then u4 by u3. So consecutive terms, that means one term after another you are taking. Okay. So if you create a sequence like this, then you take the limit of that sequence. That sequence, if you take the limit and you say this is L, suppose I name it as or denote it as a symbol L, then depending on the nature of L, I can comment about the convergence of the original sequence. Okay, so these are the two conditions which have to be checked over this L. If L is lying between 0 and 1 with equality on the holding on the side of 0, then the original sequence is a null sequence. That means it is convergent. First of all, this is convergent and it converges to 0. So two informations I can say, or I can prove rather, if L is of this nature. Again, if L is greater than 1, so you see starting from 0 up to any positive number I am saying. Okay? So if L is greater than 1, then the original sequence is properly divergent. Limit n tends to infinity un equals to infinity is what? It is going on increasing and you cannot stop it. Going on increasing, why I am saying? Because it was given a positive sequence. So no question of becoming lesser than 0. It is going on increasing above 0. That means no upper bound on it can be provided by any positive number. That means it properly diverges to plus E3. So this is the case here. When it will be occurring, it will be occurring if A is greater than 1. Okay, so one thing you see here, this was a sequence, original sequence which was provided to us. Nothing was said about whether it was convergent or it was divergent or it was oscillating. Nothing was said. Okay. Only one thing was said: this sequence consists of only positive real numbers, only positive numbers. Okay. Now, what did we do? We created a new sequence. Forget about this limit. You just think about a sequence where I am creating it by say un plus 1 by un. That means, as I said, u2 by u1, u3 by u2, u4 by u3. So these are the new sequence terms you are taking. Okay. So this now sequence, some information is provided about this new sequence. What we say is the new sequence which we are getting from the original sequence by taking the ratio of consecutive terms. That sequence, so suppose it is limit of that sequence I am taking to be L. Okay. So that sequence is convergent. I am taking it to be convergent, having the real number L as the limit. Now, depending on the range of this limit, the new sequence, I can comment about the convergence or divergence of the original sequence. So it is a one sort of via we are doing. We cannot directly say about it, but using some information from this new sequence created from the by taking ratio of the older sequence, that is the original sequence, I can say something about the original sequence. So from that respect, this result is important. And another thing you see, L, I am just seeing just two conditions. And in both the conditions, one thing is clear, L is greater than 0. Why this is so? Because this is obvious. Why you see, UN was a sequence of positive numbers. So whenever you are trying to create or trying to take ratio of those positive numbers, it is impossible that you will get a negative number. So obviously, if you are just dealing with these ratios, you are actually dealing with the ratio of positive numbers. Now, if you are dealing with the ratio of positive numbers and you are claiming it to be convergent to L, it is impossible that this sequence of positive numbers will converge to negative numbers. Impossible. The definition will not go. Okay. So obviously, it is a fact. L is greater than equal to 0. Now, L greater than equal to 0. If I get that thing out, then the only possibility is given it is either less than 1 or it is greater than 1. So both of them are covered under two separate conditions. And depending on these two separate conditions, whether L is lying on the left hand side of 1 or it is lying on the right hand side of 1, whether the original sequence is convergent or it is properly divergent. So this is the thing. Let us have a quick look to the proof. So as usual, we choose any positive epsilon. Here, other than the usual approach, we take care of another thing. What is that thing? You see, L is given to be, we are doing the first case. So L is given to be lying between 0 and 1. Lying to be 0 and 1. So now I choose epsilon in such a way such that even if you add epsilon with this L, till then, say I add epsilon with L, so L plus epsilon with a new number, I name it as L dash. L dash is still less than 1. So how is this possible? This is possible on the choice of epsilon you take. That's why it is said this is a specific choice of epsilon I am choosing. I am choosing epsilon in such a way that even if you add this much amount of positive number or this much amount of positive quantity to this L, which was less than 1, still it is less than 1. So epsilon is such epsilon we are taking. Why suddenly we are taking or we are concerning such a biasness over epsilon? We will just soon see here why this is required. So now it is given is limit intense infinity un plus 1 by un equal to a. This is given. Okay. So we just apply the definition of the limit. Okay, because this is also a sequence as I said. So obviously using the definition there is a natural number k. So please mention here k is depending on epsilon such that this happens to be true. That means the standard definition only the mod is simplified un plus 1 by un minus l. If you take mod, then you should be getting less than epsilon. That means if you break the modulus, that is absolute value, if you decode it or if you simplify it, you will get this thing. And this holds true for all n greater than equal to k. Okay. Now I'm just using the notation L plus epsilon equal to R. Okay. Then obviously, as I have taken here L plus epsilon to be less than 1, so my R is less than 1. And obviously it is positive because epsilon positive, L positive. So R is lying between 0 and 1. So this quantity for any n greater than equal to k, as I have written here, it is less than R. Okay. So, and this is true for any n greater than equal to k. So it is true for n equal to k. It is true for n equal to k plus 1, for k plus n equal to k plus 2, and it goes on. Okay. So let us now take some numbers. Just put some numbers first to show the recurrence. So I take from k n equal to k. So for n equal to k, it is uk plus 1 by uk. It is less than R. Then n equal to k plus 1. So uk plus 2 by uk plus 1. This is also less than R. And this continues up to n. Then n equal to n I am taking as recurrence formula. Okay. So un plus 1 by un. or rather here they are not taking up to n, they are taking say up to n minus 1. So suppose I put here n minus, or you're taking this whole thing up to say n minus 1 you can take here. Okay. So if I take up to n minus 1, then what happens here? N minus 1 plus 1, so un, and here un minus 1. Okay. So this that is also less than and for all n greater than equal to k plus 1. So one thing you see, it is not the case that I am stopping at n. I am just writing a few elements, a few quantities, and this is going to continue for n tending towards infinity. Okay. Why I am just writing a few terms? Because that whenever I will be using this in the below steps, you can just see whatever is asked to prove, that will come very obviously. Okay. So what I am doing here, I am just now multiplying all these inequalities. So once you multiply all these inequalities, what will happen? The left hand side will get multiplied, the right hand side will get multiplied. In the right hand side, there is only r in each of these. So how many terms you are taking here? For all n greater than equal to k plus 1, I am taking this. So here I am getting n minus k terms. Okay. So I put n equal to k, n equal to k plus 1 up to n minus 1. So k plus 1 up to k plus 2 up to n minus 1 I am taking. Okay. So here I am getting n minus k terms. N minus k times I am taking this inequality. So r to the power n minus k. Okay. And what is on this side happening? I am just multiplying this one with this one with this one like this. So now you see, once you multiply this and this cancels out. Again, if you take uk plus 2 by uk plus, sorry, uk plus 3 by uk plus 2 in the next term, after this, the next inequality will be uk plus 3 by uk plus 2 by uk plus 2 less than r. Okay, so if you not take that, then uk plus 2 will also get cancelled. And this continues. What will remain? uk will remain in the denominator because it will not get cancelled anymore. And here un remains in the numerator. It will be better if you write it a few terms on your own. You can just simply check. Nothing hard in it. Okay. So un plus un by uk we are getting less than r to the power n minus. Okay. So un less than uk by r to the power k into r to the power n. Why suddenly I just segregated or separated these two terms? Because one is including this n, which is going on increasing, and another is constant, because k is some fixed positive natural number. You have obtained it depending on this epsilon. So once I start with it, it is fixed. It will not change. But n will go on changing because n is any natural number you are taking greater than equal to k plus 1. So I segregate that part or the expression which is not at all varying with n, and this part which is varying with n. Okay. So uk by r to the power k is a fixed constant. Okay. So it is suppose I take as a fixed constant say capital N times r to the power n. Now r to the power n means what? R is a number which is less than 1, greater than 0. So if you just take r to the power n, then that is the sequence which will be converging towards 0, because it is lying between 0 and 1. Okay. So this converges to 0. Okay. So as a result of it, and this is a fixed positive number. Okay. And your un is less than this Rn into some fixed positive number. So if this is going towards 0, then obviously un should be going towards 0, because on the left hand side it is, as it is positive, so it is obviously greater than 0 for any n you take. So it is greater than 0. Again, it is on the left hand side, it is greater than 0. On the right hand side also you are getting 0. It is greater than 0, it is less than 0. So by Sandwich theorem, your un is taking to be 0. You recall that the Sandwich theorem, what was it? If three sequences were supposed to be given xn, yn, zn, such that yn lies in between xn and zn, once n is greater than some positive constant or positive natural number, this is natural number, I am taking say n greater than n. So if xn less than yn less than zn is the relation, and if xn and zn goes towards limit l, then obviously the middle sequence yn should also go towards it. Just the same thing is happening there. Un is remaining sandwiched between 0. Here it is not shown here, actually it is greater than 0, because it is positive sequence. So 0 on the left hand side, so 0 sequence is a constant sequence. On the left hand side you are getting, and on the other side you are getting some, forget about this positive constant, as it is positive we need not be thinking about it, only r to the power n. So this is again a sequence which is converging towards. So this sequence is sandwiched between 0 and r to the power n. 0 goes converges to a 0 sequence, 0 sequence converges to a 0, and r to the power n converges to a 0. So as a result of it, even is obviously converges towards 0 by the Sandwich theorem. Okay, so this is the result we are getting as is claimed in the theorem. Okay, now let us take the second case. That means L greater than F, greater than 1. Okay, now again we will have to can choose any epsilon. Now we will choose an epsilon in such a way. See, epsilon is positive number, L is also a positive number. So epsilon is chosen in such a way that even if you subtract epsilon amount from L, it will still remain greater than 1. So I have started with something which is greater than 1, and then from there I am subtracting the positive quantity. It may happen it becomes less than 1. But I am restricting my epsilon to such a values or to such values rather, such that even if you subtract those amount of epsilons from A, it still remains greater than 1. Yeah. So that is the starting point here. So let us start with this thing. Okay. Since again this is given already, again you can apply the definition. You can get a natural number m such that this holds. Okay. So now let L minus epsilon is denoted as smallest. Now S is again greater than 1 because of our choice of epsilon I have taken. L minus epsilon greater than 1, so obviously S greater than 1. Okay. So again un plus 1 by un is greater than S from here, this side. Okay. Okay. For all n greater than equal to m, you are getting this thing. Okay. Now again you write like that. n equal to m you take m plus 1, m plus 2 up to n minus 1 you are taking. Okay. So you are going to get this thing again and again. Then you again apply the thing. You multiply all these inequalities. So once you multiply all these inequalities, as we have discussed above, here you also you are going to get this sort of thing. Un by un greater than is equal to n minus 1, n minus n. So again we will segregate those terms which is dependent on n and those terms which are independent of it. That means which is constant for fixed constant. Okay. So um greater than um by s to the power n. So this part is constant, fixed constant, and s to the power n here it is directly n. Okay. Now again you see what is n? S. S is greater than 1. And this greater than 1, now you are going on taking s to the power 1, s to the power 2, s to the power 3 like this. So it is going on increasing. That means it is going towards infinity. That means it is diverging. Only because it is greater than 1. So that now you see this part is going towards infinity. This is a fixed positive constant, and whatever sequence we were dealing with, that is the original sequence, is better than this right hand side. Okay, where you are getting on right hand side you are going towards infinity, and something your un is greater than that quantity also. So obviously the un sequence also converging, also diverging towards plus infinity, because suppose I am saying this right hand side I am getting a number 10,000. So un is greater than 10,000. Again for some n you are getting 10 lakhs. So un is greater than 10 lakhs, and this goes on increasing. So you cannot bound your un. Okay. So as soon as I cannot bound my un, so obviously un is properly diverging towards plus infinity. Okay. So you are getting this. Now you see the theorem now we have in our hand. One thing has to be taken care of. What is the thing they are saying? Suppose this ratio sequence, which we have created from the original sequence UN, if it converges to 1, what will happen? That means you just simply see here, I have taken L as greater than equal to 0, less than 1, L greater than 1. These two cases discussed. But one thing is left out. What is that thing? L equal to 1 is left out. Why is left out? We will just see we cannot say specifically what will happen if L exactly equal to 1. That means if limit over n un plus 1 by un is equals to 1, then we cannot say whether the original sequence is convergent or not convergent. That means for some sequences it will be converging, for some sequences it will be diverging, in case it is n equal to 1. So for that specific case they are separating out, because that cannot be proved in general because of this oscillatory or changing nature. Okay, so they are giving some specific examples in support of it. So if un equals to n plus 1 by n, if you take, so un plus 1 by un, if simply if you just calculate, you will get 1. So obviously while it is going to 1. But this sequence 1 n plus 1 by n means 1 plus 1 by n. Okay. If you take now limit, what you will get? You will get 1 only, because 1 by n will vanish if n tends to infinity. So limit n tends to infinity, un is 1. So it is convergent, right? Now if you take un equals to 1 by n, okay, if un equals to 1 by n, then also it is 1. And where it is converging? it is converging towards 0. So we cannot say in specification what will be the limit and what will be the limit of this original sequence. Here you are getting 1, here you are getting 0. Okay. So for that, whenever you are just dealing with the case key, this sequence, this ratio sequence is having limit 1, then no definite conclusion can be given about the nature of the original sequence. Now, another similar sort of theory exists. Again, you are considering sequence of positive numbers. Now, instead of taking or instead of constructing a sequence with ratio of the original sequence consecutive numbers, I am now taking the root over to the power of 1 by n. Okay. So I am taking un to the power of 1 by n sequence as a new sequence. Okay. And it is giving me this new sequence is converting towards L. Again, depending on the nature of this L, it's the same sort of nature division is here. Obviously, because it is positive number, as I already said, so L is obviously greater than 0. So this is one case. If this is the case, then this even goes to 0. And if L greater than 1, then even goes to infinity. That means it is not divergent. Sorry, it is not. It is properly divergent. It was converted. Okay. So let us see the proof. Here also the almost the same strategy. I choose some epsilon so that even if you add those epsilon amount to this positive quantity, it still remains less than 1. Okay. So with that thing, and again applying the definition of this one given, you will find some natural number k depending on epsilon. Please mention that k depending on epsilon. You are going to get just writing down the definition. Okay, so this thing is obvious. Now I take this one as a noted or denote this one as r. So I take this r. So r is less than 1 and greater than 0. And given this quantity is less than r from here, from this part of the inequality. Okay, for any n you are taking to be greater than equal to k. Okay, so un is lying between 0 and r to the power n for all n greater than equal to k. Because you are just taking even to the power 1 by n, if it is less than r, both of them are positive. So even less than r to the power n, simply just you are just multiplying n times. So this will come. Now this is set to be 0. Again, so by sandwich theorem, see here it is 0 on the left hand side. It is also going towards 0. So it is a constant sequence going towards 0. It is a sequence which is going towards 0. So by sandwich theorem, again my un will be going towards 0. So the first part is proved. Now the second part, where L is greater than 1, again the same strategy. I will choose epsilon in such a way so that even if I subtract epsilon amount from L, L minus epsilon still remains greater than 1. Okay. So I choose like this. Again, you apply the definition of this which is given. So you find the natural number m such that you can just write down the definition again. So this is the thing. But L minus epsilon, let me denote as S. So this part, now this part. Okay. So you can just simply note down here for the first case I am taking this part of the inequality. For the second case I am taking this part of the inequality. Okay. So this thing is greater than 1. So this one is greater than S from this part. Okay. Just this one. So un, if you just multiply n times, obviously you will get un greater than S to the power n. But S is greater than 1 quantity. So you are going on increasing the exponent, as I already said in the previous theorem also. Any greater than 1 quantity, you are going on increasing exponent. Say I am starting with S equal to simply say 1 by 2. Suppose I take S equal to 2. First you are taking 2, 2 to the power 1, 2, then 2 to the power 2, 4, then 2 to the power 3, 8, and this continues to be increased. Okay. Now my original sequence is greater than that increasing quantity also. So this increasing quantity itself cannot be stopped, or itself cannot be bounded. Then obviously this quantity also cannot be bounded. That's what we have discussed in the previous theorem. So here my un diverges towards plus infinity. So again here the same case. We have left out the only possibility what will happen if L equal to 1. That cannot be covered under this theorem. If L equal to 1, no definite conclusion. As we have given here the example, for L equal to 1, one sequence you are getting converging towards 0. Another sequence you are getting which is not at all converging towards 0. Okay. Here also one such example needs to be provided. Okay. So this example they have provided here, where this nature is varying. Okay, when your UPN to the power 1 by n sequence is having the limit value 1. So now with this, we have done some of the results related to the sequences. Now let us have a look at the monotone sequence definition. So monotone sequence means, as the name suggests, the monotonic, there is the monotonic nature in it. Monotonic means what? Suppose consider the sequence n. Only the sequence n if I consider. So what are the elements? 1, 2, 3, 4. So as you can see, simply see, if you are taking the first element 1, the second element 2, then third element 3. So if you are going on increasing the ordering, the suffix of the sequence, the numbers are going on increasing. That means if you are going on increasing the natural number, the corresponding elements are going on increasing. Okay. So that is the monotonic increasing sequence. Again, if you simply take minus n, just the opposite nature you get. -1, -2, -3, -4. So -1 is x1, -2 is x2, -3 is x3. So x1 is greater than x2, x2 is greater than x3. So as I approach writing on the numbers are going on decreasing. Okay, so that is an example of decreasing sequence. So let us give a formal definition. So what is the formal definition? Say a real sequence Fn, obviously a real sequence because complex numbers cannot be ordered. Okay. So a real sequence Fn is said to be monotone increasing sequence if, as I said, if you increase the suffix, your sequence element will be increasing. Increase the suffix means it is a function of n. So n plus 1 if I take, it is greater than n. So correspondingly the element should also be greater following the same relation. So f of n plus 1 should be greater than equal to f of n. Okay. So this is monotonic increasing sequence definition. Similarly, monotonic decreasing sequence is just the opposite. N plus 1 is greater than n, but once I take the sequence elements, that means f of n plus 1, it is following the reverse order. That means f of n plus 1 less than equal to f. So in case any sequence is of the nature either this one or this one throughout for any n, then only it is said to be the monotone sequence. Okay. So why I am saying every time for any n? Because some sequences may be such it is not of that case. That means it is not following this relation throughout for all n, or it is not following this relation throughout for all n. Suppose for some n it is following this relation, and for some other n it is following this relation. Then that is changing the nature, right? So there is no uniformity in the nature. That is, you cannot say it is going on increasing directly, or you cannot say it is going on decreasing directly. It is changing nature. That means it is of oscillatory nature. In that sense, it is not at all a monotone sequence. If it is a monotone sequence, it needs to be monotone increasing throughout. Throughout means whenever I say monotone increasing, obviously, as in the definition also you can see they are mentioned for all n. This is very crucial. You cannot just miss this thing for all n. Because in case if some sequences may be there, obviously if you take two numbers, obviously one is going to be greater than the other. And if you take other two numbers, that relation may be reversed. So this is very important. If you say it is monotone increasing or monotone decreasing, then for all n you have to mention. Otherwise it becomes meaningless. Okay? So if you take strictly, that means this equality is prohibited or omitted, then you get a strict sequence. That is strictly monotone increasing if of n plus 1 greater than fn, and strictly monotone decreasing if of n plus 1 less than fn. Okay. Another thing, if for some natural number m, f of n plus 1 greater than equal to fn, for all n greater than equal to m, then we say fn is said to be ultimately monotone increasing sequence. Now one thing you see here, so what is the difference if I compare this definition with the standard definition given at the very beginning? What I said here, it is monotone sequence, right? So it is holding, this relation is holding good for any n input. Now it may happen, as I already said, for all sequences this is not the case. So some sequences, now let us focus or let us consider where once you cross some natural number, say m, once you cross some natural number m, then this result is holding good. So before m, I cannot say whether this relation is holding good or not. Maybe it is holding good, may not be it is holding good. Maybe it is holding good for some n less than m. Maybe it is holding That's the opposite for sum and less than n. So I am not concerned about the right hand left hand side of it. But once I cross this m, so suppose m is 10. So for all n greater than equal to 10, this relation should be equal. So for all n less than 10, that means for 1, 2, 3, 4, 5, up to 9, it may have been key. This for some it is true and for some it is not true. Okay. So we are not bothering about that. But once I cross n greater than equal to 10, then this should be holding good. If this is the case, then it is said to be ultimately monotone increasing. Ultimately means what? After some barrier, once you cross that barrier, no matter to think what number you are, what natural number you are taking, once you cross this barrier, this equation is holding good. So it is ultimately monotone increasing sequence, not monotone increasing sequence, but ultimately monotone. Because below that there may be some change in the nature, or there may be some case where this is not holding good. Similarly is the case for ultimately monotone decreasing sequence. Again, if you cross some barrier of the natural numbers, this is holding true for any m greater than equal to m. But below m, I cannot see whether it is holding true or not. Then they are provided with fn equal to 2 to the power n. As I said, just simply see f of n plus 1 is what? 2 to the power n plus 1. But 2 to the power n plus 1 is greater than 2 to the power n for any n you take. Okay? Any natural number you take. So this is the monotone increasing sequence. Similarly, if you take this number, if n equals to this, summation 1 by n plus 1 plus 1 by n plus 2 up to 1 plus n plus n, 1 by n plus n. So if of n plus 1 minus if n is a constant. So if of n plus 1 means what? I will get here 2n plus 1 plus 2n plus 2 minus n plus 1. If you just simply write it out, for n, here it is up to n you are saying. So n plus n is the last term. If I take n plus 1, what will be the last term? N plus 1, so 2n plus 1. So this is the thing. Okay. Plus 2n plus 2 also will be coming. Minus 1 by n plus 1 from this part. Okay. So as a whole, I am getting this part. But it is greater than 0. Okay. So if n plus 1 is greater than n. So again it is monotone increasing. Okay. Now if you take this sequence 1 by n, f of n plus 1 minus fn, you will just see 1 by n plus 1 minus 1 by n. So you just simply calculate it, you will get less than 0. So this is a monotone decreasing. Now you see this sequence minus 2 to the power n. It is neither a monotone increasing sequence, not a monotone decreasing sequence. If you break it for n equal to 1, what you will get? Minus 2. N equal to 2, 4. N equal to 3, minus 8. Then n equal to 4, 16. So minus 2, 4, minus 8, 16. You cannot say. Once it is going on the negative side of the origin, or negative side of the x-axis on one, or as for other values, it is going on the positive side of the x-axis. So it is changing nature. So neither you can say this is holding true, nor you can say the opposite is holding true. Okay. So if this relation is not at all satisfied throughout any n or any barrier of n crossed, so obviously it is neither a monotone increasing sequence nor a monotone decreasing sequence. Now another result which is important in this case, a monotone increasing sequence, okay, if bounded above, is convergent and it converges to the least upper bound. Okay. So if fn be a monotone increasing sequence which is bounded above, okay, and let m be its least upper bound, okay, then in that case fn is less than equal to m, quite obviously, because m is, you are saying, to be least upper bound, and this least upper bound, obviously you have the, for the general students I am speaking, this least upper bound you have the idea from the previous semester part of your syllabus. Okay, so I'm not going to repeat it, and for the honor students you are having this in your this semester course. Okay, and we have already discussed in details what we mean by least upper bound. Just a thing you have to keep in mind, it is an upper bound, and all the upper bounds, this is the least one, the smallest one. Okay. So for that thing, I am taking the monotone increasing sequence bounded above m as the least upper bound. So obviously any number, any element you are taking for the sequence, it is less than equal to m, and any positive epsilon amount if you decrease from m, definitely by the property of least upper bound, I will get at least one natural number k such that fk is greater than m minus epsilon. That means what? As m, capital M is my least upper bound, so if I decrease this minimum amount also, a very small amount also from m, that means m minus epsilon I am taking, I will get at least one sequential element, or at least one element of the sequence which will be greater than m minus epsilon, as m was the least upper bound. Okay. So if k, corresponding to that, I have chosen say k as the natural number. So if k is an element of this fn sequence, so if k greater than m minus epsilon. Okay. Now you have said ki fn is a mod on increasing sequence, right? So fk less than equal to fk plus 1, as this is mod on increasing, but fk is greater than m minus epsilon, okay, because of this part, and fk less than equal to fk plus 1 less than equal to fk plus 2, and this continues, and ultimately it is bounded by capital M. So now you take m minus epsilon fn. So in general I can write fn because this is going on continuing for any n greater than equal to k. So m minus epsilon less than fn less than m plus epsilon, because m is again less than m plus epsilon, okay, because epsilon is a positive quantity. Okay, so m minus epsilon less than fn less than m plus epsilon for any n greater than equal to k. This means what? Fn is satisfying the definition of convergence, converging towards what? Towards m. That is what they have claimed. If you take a mod on increasing sequence, that is fn is a mod on increasing sequence which is bounded above, because capital M is there I am taken, so it converges to the least upper bound. So capital M was least upper bound, it is indeed just converging towards this least upper bound. So this is true. Similarly, if you just take a mod on decreasing sequence, I am not going into the details to complete, exactly the same procedure you have to follow. So mod on decreasing sequence if you want to take, which is bounded below, okay, is going on decreasing, and it is bounded below by some real number. Okay, then obviously the sequence is bounded, and it converges. It's obvious the sequence is convergent, and it converges to the greatest lower bound. So this is the case. The mod on decreasing sequence is bounded below, is convergent, and it converges to the greatest lower bound. For the general student that you mentioned, the proof you may omit, okay, but the result you have to keep in mind, so as to be used in some problems. Okay, the result obviously you have to is a part of your syllabus. The proof you may omit. Okay. Now for the mod on increasing sequence, another theorem says mod on increasing sequence which is bounded above diverges to plus infinity. It is quite obvious. The sequence is going on increasing, and on the increasing side you cannot put a boundary, then obviously it cannot be stopped. It cannot be stopped means what? It will go on increasing. That means it will properly diverge towards plus infinity. So similar is the case if you take mod on decreasing, that is unbounded below, it will go on decreasing. You cannot stop it below. That means it will go on decreasing, ultimately it will properly diverge towards minus infinity. So that is the last result. Mod on decreasing sequence, that is unbounded below, diverges towards minus infinity. Okay. So again for the general students, you may skip the proof if you want to, but the result you have to keep in mind. So let me just have a look at the proof. So if fn be a mod on increasing sequence I am taking, which is not bounded above. Now not bounded above means what? Whenever I am trying to put some boundary, it is failing. That means what? Whenever I am trying to put some boundary means what? I am trying to choose or trying to select some real number, say capital M or whatever, and saying ki my fn is less than that amount. Say they have chosen here G. I'm always failing to do so. So suppose I choose capital M or G equals to 10,000. I find some sequence elements which is greater than 10,000. Then I thought, okay, 10,000 is smaller, let me take 10 to the power 6. Then again I find some sequence elements which is greater than 10 to the power 6. Then again I increase 10 to the power 12. Again I get some sequence elements which is greater than 10 to the power 12. And this continues. You cannot get any boundary. So that means what? That means for any pre-assigned positive number G, such as I am choosing 10 to the power 6, 10 to the power 12, 10 to the power 14, like that, for any pre-assigned positive number G, however large, as I am choosing also, there exists always a natural number K such that Fk is greater than. As I said, whatever, no matter what number you are choosing, you are always getting a sequence element which is crossing that number. That means that is what they are saying. There exists a natural number K such that Fk is greater than G. Now we are saying keyword. Your sequence is increasing. So Fk plus 1 is greater than Fk. Again Fk plus 2 is still greater than Fk plus 1. Again Fk plus 3 is still greater than Fk. Okay. Fk plus 2, and this goes on. So as we move along the right hand side, you can simply see all of them are greater than G. Okay. So definitely you cannot bound it. So definitely it is going to diverge towards plus infinity. Similarly, for the decreasing sequence, the same thing happens. Only there exists a positive number g, however large, such that you find a natural number k or say k dash such that if k is less than minus g, because it is unbounded below, you are saying. So if k less than minus g in that case, but if your sequence is monotone decreasing, so all these numbers will reverse minus g greater than fk greater than equals to minus fk plus 1 greater than equals to, sorry, not minus, so minus g greater than fk greater than equal to fk plus 1 greater than equal to fk plus 2, and this continues. So all these numbers are smaller than minus g, right? In this case, all these numbers are smaller than minus g. So obviously we cannot put a bound on the lower side. That means it is unbounded below and it goes on diverging towards minus infinity. So this is the case. So let us stop here.